Hi everyone, my name is Raina, and today I will be presenting our progress thus far on our project, Dislocation Properties and Mobilities in Titanium via Molecular Dynamics Simulations. I would first like to thank my sponsors, Los Alamos National Laboratory and the online REU program at Texas A&M University, as well as my mentors, Dr. Dung, Dr. Nuttall, and Dr. Fenson. Since we are studying dislocations in titanium, some background on the importance of this. Specifically, we're looking at titanium because it has high strength, low weight, so it's used in many applications, such as in the aerospace or automotive industries. As shown in the figure on the left, titanium is widely used on aircraft. Dislocations are a type of material defect, so not all materials in life consist of perfect crystals, so there are always going to be defects. They are the weak points of the material, and failure is often caused by the defect moving as opposed to every atom's bond breaking. Dislocations especially grow and move as a material is deformed. So studying the properties of dislocations as we deform titanium allows us to better understand its failure mechanisms to prevent situations like these on the right. We are using simulations for this. So why simulations? There are no easy analytical solutions to most problems, and physical experiments are extremely difficult to control. This is a video of dislocations moving through a material. As you can see, they move very quickly. So once they get going, they disappear pretty quickly. And not only are you looking at something very small, but it's also occurring in a very short amount of time. So that's a very small window of observation, and simulations are much easier to control and study the results of. The figure on the right shows simulation methods for different length and time scales. So for studying dislocations, looking at individual atoms, we typically deal with the picosecond, microsecond scale, and for time and for length, microns. These are tiny, but simulations allow us to see that very local behavior. So the simulation method we're using is molecular dynamics. So in molecular dynamics, all the atoms are treated as point masses that interact with each other. This figure below briefly shows the steps involved. So firstly, it requires inputs, including the interatomic potential and some initial and boundary conditions, such as initial position and initial velocity. So it takes those conditions and for a small time step, integrates the equations of motion and outputs quantities like temperature. It also solves for new conditions, so new position, new velocity, and that is used as the new initial condition for the next time step. So then it integrates the equations of motion again, and it keeps going for each small time step, and as a result, you get data for how atoms behave as a function of time. So a brief overview of LAMPS, the code I'm using to run the simulations, created by Sandia National Laboratory. So it is open source, and there are many resources out there. Here's an example of some lines of code. As you can see, you have many control of many parameters, and LAMPS is really good for large-scale problems too. So simulations that require lots of computing, like ours, which is why we're using Texas A&M's advanced computing resources. So the first step in my research was to get comfortable with the software and the process. I examined an example with aluminum. So as I mentioned, there are lots of LAMPS resources, so I used and modified an example from a Mississippi State University tutorial. I ran different LAMPS files through the supercomputers, changing parameters, seeing how those changes affected results by using Python to interpret the data, and a few examples are on this slide. So the animation here shows aluminum experiencing tension in the horizontal or X direction, and this animation is possible due to having data of the atom's positions over time. So the colors represent different crystal structures. So colors that aren't green represent dislocations that are forming. On the left, we have a graph showing temperature converging for different damping coefficients. I set the temperature to 300 Kelvin in this case, but it takes time for it to converge, and how quickly it converges depends on the damping coefficient, Tdamp, set in this line of code. So for different values, they converge at different rates. On the right, I have the stress-strain curve for 3 temperatures. You can see the curves are very temperature dependent, and that makes sense because temperature affects the ductility of materials, which affects how easy it is to strain a material. To conclude, the key takeaways are that dislocations in titanium are important to understand, and molecular dynamic simulations are a powerful tool for examining local behavior of atoms. The next steps are to apply the same process I did with aluminum, but with titanium. So again, I'm using LAMPS and molecular dynamics, but I will be changing parameters and seeing how they affect dislocations. If time allows, we will specifically look at the mobility of an isolated dislocation, so how it moves, how quickly it moves. That is the end of my presentation. Thank you very much.